please, Anna.
Thank you. So I hope it will be short because the result is very short and it is not very serious. I just wanted to look at the following question.
We cannot hear you.
Anna, yes, it was better before.
Sorry, just a moment.
All right.
I understand what happens. Normally it's...
Is it better?
Not really. It's loud, but not clear.
Okay, I'm really sorry. Maybe I need 1 minute to switch the network.
Okay.
To switch to another network. Sorry. Just a moment. It is strange. So is it better now?
Yes, it is.
Please. I'm very sorry. Just
It's fine.
So I hope I can continue. So the initial question was as follows. If you have an ordered alphabet and a morphism on it, and two words, like two infinite words, or finite words if the order is well defined, one of them is less than the other lexicographically. So what can we say about the order between their images, phi images of U and V? So it is very well when the order is preserved. Like, for example, for the two morphism, if you can prove that if one word is less than the other, then the images are in the same order. So it is not a serious result. We can see it more or less instantly. By the way, I'm really sorry. It seems that I do not record it because I do not record my talk.
Someone is recording.
It's okay, Manon's recording.
Yes, I am.
Sharing many roles at the same time is complicated. Sorry. So it is order preserved like this. And so this is the definition of a morphism to be order preserved. Just the order is always the same. And if the morphism is order preserved, it is nice in some sense. But it is not always the case. For example, if we take the period Dublin morphism, we have always the opposite order. The image of A is less than the image of, is greater than the image of B. So we can say that this morphism is order reversing because the order is reversed. So here everything is very simple. Everything is binary. Another morphism which is almost as simple is the Fibonacci one. The only difference is that here one image of letter is a prefix of the other, and so we should think a little bit more, but just a little bit. We see that the image of A always starts, the image of a word which starts from A always starts with AB, and the image of a word which starts with B always starts with AA. So it's order reversing the Fibonacci morphism. But we can also check that its square is order preserving. So if we need something order preserving, it is here. We should just take the square. So in fact, it is a recent small and nice result by Borcher and Rampersad that in the binary case, any morphism is either order preserving or order reversing. And of course, if it is order reversing, then its square is order preserving. So the binary case is simple. The order is always either the same or the opposite, nothing more. If the images of letters are not prefixes one of the other, then it is obvious. So we need a proof only if it's not the case, like for the Fibonacci morphism, if one of the images of letters is the prefix of the other. And the proof is not very long. So we used this result with Melody and Rio in our paper, which was, in the paper, there was a result on order-preserving morphisms, and this result allows us to use it for any binary morphism. But of course, the next question is what exactly happens if the morphism is not binary, if we have a greater alphabet? Of course, it is easy to construct a morphism which is not order preserving nor order reversing, but can we say that something about its powers, for example? Is there a power which is order preserving? So it would have been nice if yes, but unfortunately the answer is negative. So for example, if you take this morphism, it's easy to check that the image of A is always greater than the image of B for psi square, for any powers of psi. There is this inverse order which is preserved all the time. It is possible only because we have 3 letters here, not 2, but we cannot avoid things like this. So the motivation of my very small study was to understand what exactly happens for greater alphabets. What are the cases we can meet? And here is a kind of description of how we can describe what happens. The result is not very nice. We just understand that there is a finite number of possibilities, even if this finite number is huge. So, and instead of giving a formal definition, I just give you an example. So, sorry, I did not say that, unfortunately, the situation is rather complicated, even in the case when the phi images of letters are not prefixes one of another. So it's a prefix-free morphism. Even in this case, which is trivial in the binary case, here there is something to do. So this is an example of what may happen. So this is a more or less arbitrary square-free morphism over phi of letters. We see that all the images of letters start with the same letter A, so it is not very important which letter it is. What is important is that the images of A and C diverge from the images of 3 other letters. At the second symbol, the second symbol can be D or E, so it is the first point where something differs. So it is an important point, and we write down somewhere these blue letters. Then, for example, if this letter was D, then the images diverge at the next symbol, which is B or C. If the letter was E, then there is the next letter, which is not interesting, which does not add anything. And there is some difference in red letters A or D. So every time we color a letter which adds new information about the order, and then we write something with only colored letters, like this. So we just erase from this initial morphism the letters which do not add new information about the order of images of symbols. And what we got is called the trimmed morphism, phi trimmed. So the main idea is that it's sufficient to consider such morphisms and their powers, and not only their powers, but their trimmed powers. And everything will be described. So it's a simple idea, in fact. So by the construction, the trimmed version induces the same order of images of letters. Then we can prove, and the proof is not complicated, that if we have a composition of morphisms, and we have a composition of trimmed morphisms, then the trimmed result is the same, and it just explains the order of what happens for the composition. So we can denote this new operation. So trimmed morphism times trimmed morphism and then trimmed once again, we can call it a star operation over the set of trimmed morphisms. And this is a semigroup operation, in fact. So then, since in trimmed morphisms, we only write letters which give some divergence between images of letters, we always write down a finite number of letters. We can give an estimate how many. So it's a finite number of letters. So there is a finite number, it's a bounded number of letters for any given alphabet. So for any given alphabet, there is a finite number of trimmed morphisms. So it is a finite, but huge monoid, because there are many the trimmed morphisms. But if we study the properties of this monoid, we can describe everything what happens for the orders of words under a morphism. So since it is huge, then it means that the powers of every element form an ultimately periodic sequence. So in some sense, everything for any given morphism, the sequence of orders which induces over images of letters, this sequence is ultimately periodic. So in fact, the trimmed morphism gives exactly more information than images of than the orders. Maybe the period of the sequence of orders will be smaller, but anyway, it will be there will be a period. So just several more examples. For example, if a morphism is marked in Francesca terms, or even if there is a one common prefix and then a permutation of letters, then its trimmed version is just this permutation of letters. And so among trimmed morphisms, in some sense, there are all permutations. There are also some longer and nastier things. So the longest possible situation is when the images of symbols separate from each other one by one. So for example, the image of first letter, maybe after some common prefix, there is a different letter just for one symbol. For the others, there is the other letter. Then there is just the second symbol, which diverges from the others somewhere else, and so on and so on. So at last, we may have an image of symbol in a trimmed morphism of length n-1. It may happen. And it is the longest possible situation. And then if we are looking for a typical example, maybe this example will be too much typical, just a ternary morphism. So its trimmed version is just the same, but without this last A here, because the image of C is already separated from the images of A and B, no problem. So its trimmed version is like this. It's square, the usual square in the morphic sense, the morphism of a morphism square of ABC is here. We can trim it because, okay, there is the first A, we erase it. There are C, B, which we write. Then there are BA, and there is no need in this B. So we trim, we obtain the square in the trimmed sense, in the star sense of this T of phi, and so on. So we can continue to trim the powers of this trimmed morphism. And we obtain that the fifth power is T itself. So it starts with a period of length 4. And in particular, if we study the order between images of symbols, we see that for phi itself, the smallest image of letter is the image of B, then A, then C. And we can extract all this information from the trimmed morphism. And we see that it's also a periodic sequence. In particular, here the morphism phi to the power 4 is order preserving. So if we needed something order preserving, here it exists, and we found it. In the general cases, it is not the case, as we have seen in another example. So there is just a cycle of length 4. So everything for any given morphism, we can study everything, and it is not very complicated. So, but unfortunately, what is complicated is that the number of trimmed morphisms over an n-letter alphabet is huge. So this lower bound is just the number of the longest possible trimmed morphisms of the shape when the symbols separate one by one. This upper bound is just very rough. It is more or less obvious. And I don't know what exactly happens in between. I guess it is closer to this bound. But if I tried to compute the first symbols for what happens over 1, 2, 3, 4 letters. So the first elements are one morphism, one shape of a trimmed morphism over one letter, 2 trimmed morphism corresponding to order preserving or order reversing situation for over 2 letters. Then over 3 letters, there are already 114, which are the 6 permutations and the 108 morphisms where they separate one by one. And then for n equal to 4, there are 28,000 something. So it's a sequence which grows very fast, and I don't know how to deal with it. So this sequence is not yet in the online encyclopedia because just there is no preprint, there is nothing. It is just a draft. And I mean, I looked for it. It is not there. It's something new, and maybe it's just too nasty to be included anywhere. So the next question, which can be interesting, is what is the longest period of these orders among, if you take the powers of the same morphism, what is the period of orders? We have seen 4, a period equal to 4. Can it be longer over 3 letters or not? How long can it be over 4 letters, 5, and so on? So this is a question which can be interesting, but I just know nothing about it. The lower bound for this, length of period, the length of the longest period, is the largest order of a permutation for the n. Just because permutations are particular cases of trimmed morphisms, and it is something almost exponential, like here, even for permutations, and it seems that it can be longer than for permutations in the general case, and I know nothing about it. So I am very glad that I had to talk here, because otherwise during the semester I never remember what I should do and if I should do something in mathematics. So the conclusion is that we can describe for any given morphism, for any given 2 morphisms, we can describe what exactly happens at the level of orders between images of letters, between orders between images of infinite words, if you prefer. We can describe everything with trimmed morphisms and the star operation on them. The trimmed morphisms make a huge monoid under this operation, which is composition and then trimming. It is finite, but complicated, and I don't know how to really study it. But we can study its properties if it is interesting, and we can not to study them if they are not. So that's all. Thank you.
Thank you, Anna, for the talk. Do we have any questions for Anna?
Yes. I have a question to Anna.
Sure.
You said it contains the symmetric group of the alphabet. Does it contain also the monoid of all functions from the alphabet into itself?
All functions of the alphabet into itself. It seems that I don't know, but it seems even more complicated in some sense.
Yes, but I ask for containment only. I mean, it's yes, it's bigger because your lower bound showed that it's bigger. The monoid I'm telling about has elements, has a cardinality n to power n.
So the first column, if you consider the trimmed morphism as a sequence of columns, the first column, the first symbols of it is just any function from the alphabet to itself.
Yes.
So it's a part of information, but it is not, there is no isomorphism, I guess, because it is also important what happens later.
Yes. Okay. No, I think my question was not very smart because it's evident that it contains this monoid. You just take a monoid of function of the alphabet into itself, a function from the alphabet into itself defines the morphism, which must be trimmed, I suppose.
Yes, well, it is not trimmed if it is just something like AABB. We should add how the two images of starting with A, by which letters they diverge. So we need, for the morphism to be trimmed, we need more information. We need some more columns. So I can return to a slide where there was an example of a trimmed morphism here. So for example, DE is a function of the alphabet to itself. But then if we just leave the blue column, it is not a trimmed morphism. We need to distinguish between these two Ds and among these two three Es. There is more information needed.
Mm-hmm. Okay.
Another question, maybe? Well, if not, then we can thank Anna again and all the speakers.
Thank you.
Today. And well, I guess that's it. I mean, we see each other next week. I think so, right? Yep.
Yeah.
So,
Manon, can I say that
yes.
Europe, much of Europe will enter daylight savings time
that's true.
coming Sunday, which means for people outside Europe, the time will now change back again to the time it was before 2 weeks ago for you outside Europe. So just keep that in mind. Yeah.
That's a good point. Thank you, Jeff. All right. Well, have a good week, everyone.
Thank you.
Bye.
Bye.
Bye, everyone.
Manon, good job handling the slides.
Oh my goodness.
You were completely unflustered. It was very impressive. I would have been all worried.
Easy. Oh my God.
Yeah. Very professional.
All right. Okay, good. Yeah. Is Narad here? No, he left. Okay, that's fine. Anna, maybe. Wait, I'm gonna